Unfortunately, that was poor timing. But you should get an after image when you're staring at that spot right when I turned it off. This is just a white screen, but your brain has overloaded the back of your eye with these chemicals, and so it takes a little while, a few seconds, for those chemicals to wash out again. I got another example. This one works really well too. So what I want you to do is stare right here, right at the corner of the yellow square, and just stare at that for several seconds here. And we're going to do this, and we're going to overload the chemicals in your brain. Here. And once you're staring at it for long enough, 20, 30 seconds, don't move your eyes around, just keep staring at it. Then you look, and you should get an after image of the American flag in the right colors. Now, how did I create this? Well, the after image is the exact opposite colors on a color wheel. So right here, these would become, black would become white, this blue color becomes red, and the yellow color becomes blue. So it's opposite each other on the colors spectrum. And so that's how your eye interprets, or how we interpret different light conditions. All right. Turn this off for a second. All right, so let's keep talking about light. One thing that Newton did is he took his prism and he created this really cool experiment. He said, okay, here comes sunlight. And he took his prism and he put it like this. So he put his prism here like this. And the prism breaks the light up into different colors. What really happens is the glass in here actually refracts or bends the light, and it bends it differently depending on the wavelength, which is why it separates it out. And so it separates it out, bends out the colors, and you get a whole spectrum of light from red, orange, yellow, green, blue, violet. And what he wanted to do, what Newton decided to do, was figure out, that's a Y by the way, was figure out which wavelength was the best at, or had the most ability to dry off a blotter. Remember, a blotter was a piece of paper that they used back when they used to use ink writing. And so he covered the blotter in an equal amount of water, and he laid it out here, and he was trying to figure out which color was most efficient at drying out the blotter. And what he found was that way out here, this dried the fastest. And he did it, and he did it several times. He goes, wow, so there's a spot out here that's drying faster than this. He correctly interpreted that to me, there must be wavelengths beyond what our visible eye can see. That led him to discover what we now call infrared radiation. So, let's talk about what we call the electromagnetic spectrum. The electromagnetic spectrum has visible light right in the middle. Okay? Now I'm going to flip it around here so don't get confused. I was always putting red on the other side. I'm going to put red over here and violet on this side. And we already talked about that there's wavelengths beyond red. We call this region infrared. And remember, these have longer wavelengths. These have shorter. And so as they go this way, they get longer still. So infrared rays are longer than visible light. And beyond infrared, we have microwaves. And beyond microwaves, we have radio waves. Okay? And the reality is there's no limit over here, but anything out here, a certain range of wavelengths we call radio, no matter how big it is. I mean, the wavelength could be as big as the universe, it's still a radio wave. So these radio waves have very long wavelengths. They have the longest wavelengths in the universe. they have the smallest frequency, and they have the lowest energy. Okay. Now if we go the other way, beyond visible light, we get to ultraviolet, or beyond violet. And then beyond ultraviolet, we get to X-rays, and beyond that, we get to gamma rays. These are gamma rays right here. That's the Greek letter gamma. All right, let's talk about each of these. Now, radio waves, and you see all these down here up through visible light. This is what we see with our eye. All these down here have fairly low energy. And that low energy is good because they don't hurt us, or at least we don't think they hurt us. We're not for sure what long-term exposure to certain things can do to us, and you can always create what they call power, the amount of energy coming out, and you can burn people with radio and even microwaves, even though they're lower energy. The key with that is that the radio waves typically can't penetrate your body. They don't have enough energy. They can't go through your skin, okay? But everybody nowadays has cell phones. And this started only within the last like 20 years or less, when it became a very common thing. So nobody's really quite sure if having a radio transmitter next to your head for your whole life is a good thing. So right now we are in the generation that's testing this. It may be in 20 or 30 years we find out that all these people that had cell phones from the time they were 6 years old all the way to the old, that caused some kind of damage, and maybe they'll all have brain cancer or something. We don't know. This is the first long-term study that's ever happened because you're living in this time in history. And the good thing is the radio waves, as far as we know, don't hurt us because you're getting bombarded by billions of radio waves continuously. From every cell phone, every TV station, every radio station, they're just coming continuously through and hitting you all the time. Microwaves also do not penetrate your body and hurt you. But you say, well, what about a microwave oven? Okay, that's a very special case. And this really doesn't have to do with astronomy, but I'm going to tell you how microwave oven works. What they figured out that they can do with the microwave is they can have their waves, and they can do what they call polarize the waves. They can make one like a positive and one a negative. And so what happens is, if you have a molecule like a water molecule, which has an oxygen and two hydrogens, it looks kind of like Mickey Mouse. What happens is this side of the water molecule is negatively charged, this side is positively charged. It becomes what they call a polar molecule. Well, remember, positive and positive don't like each other, so the whole molecule, the water molecule, will flip because it wants to line up the negative with the positive and positive with the negative. And then what you do is you flip the microwaves, meaning you make this one positive, and you do this one negative. You start doing this about 60 times a second. So it just starts flipping back and forth like crazy. Well, that essentially heats it up. And that's why cooking things in microwave that are water-based cook very well, like rice and pasta and stuff like that. Cooks very well because it's water-based and you can heat up the water very well. Doesn't work well when you're trying to cook things like that are mostly fat, like hamburgers or a steak. You don't want to cook your steak in the microwave, it'll taste terrible. All right? So that's how it works. And that's why things like when you put a marshmallow inside your microwave, the outside actually is sealed, but the inside has the water molecules. The microwaves penetrate that, they heat them up, they turn to steam, and your marshmallow will start to get really big. It's also the same way popcorn works. A popcorn kernel has a little bit of moisture sealed inside of it, and the microwaves penetrate that, they turn that water into steam, and then that steam gives enough pressure that it pops open. So that's how a microwave works. Now the bad thing, usually microwaves don't affect us, but don't put your head or your arm or anything in a microwave oven because you're mostly made of water too. And if that microwave can penetrate, then you're in trouble, okay? Because it starts to heat up the water in your body. Now all microwaves are made so that that's impossible. In fact, when you look at the microwave oven, there's a grid of wires in there, but you can see through the grid. The separation between those wires has to be smaller than the wavelength. So the wavelengths that the oven is using are bigger than the little holes or the little gaps in the wire mesh that's in front of your door. And all microwave ovens are made that when the door's open, it won't work. It's a safety feature. Infrared radiation we could even detect as humans. You say we don't detect it, we can't see infrared, but we can feel it. Because our body is very sensitive to infrared and we feel it as heat. It absorbs infrared very well. And so if there's something that's giving off infrared radiation, we feel that as heat, especially different parts of your body like your cheeks and stuff are more sensitive to that infrared radiation. You can feel the heat source. So something might be very hot, like if you take a poker or something out of a fire, you bring it out, well it doesn't look, you can't see it glowing anymore, but if you bring it close you can feel the heat coming off. It's still putting off a whole bunch of infrared radiation. Then we talked about visible light. Now when you get beyond visible, you get to ultraviolet. Ultraviolet is now getting high enough energy that it starts to penetrate your skin, which is why it becomes bad. That's why there's actually three parts of it. We have UVA, UVB, and UVC light. So they break ultraviolet up into three parts. The UVA stuff down here is the lower part. That's the part that comes through your skin and can give you a tan in the summer or a sunburn. The UVB penetrates even further. That's a U, by the way, doesn't look like it. And that's the bad stuff, and this is the stuff that most people think is more likely to cause cancer. Now you can still get cancer from overexposure to UVA, but UVB is worse because it's higher energy, so it can penetrate into your skin and it can cause more damage to it. UVC is just nasty stuff, and that'll just burn you, okay? But they use this ultraviolet radiation up here to sterilize instruments. And lots of places, like medical places and stuff, will have a UV and they'll put their medical tools in there, zap it with UV light, and it kills any bacteria or anything that could be on it. So it works as a way to get rid of nasty stuff. But luckily,